Okay, so welcome to the afternoon session, and our first speaker is Ekaterina Vasilyeva. Should be. I didn't memorize the talk, and now it's blocked, but I'm sure she'll tell you her title. Should I start? Sorry. So thanks for this opportunity to present my work here today. My two goals during this talk are, on the one hand, to present my recent results on quasisymmetric functions, in particular to interpolate a new way to interpolate between Gesell's fundamental quasisymmetric functions and Stambridge's peak quasisymmetric functions. And on the other hand, to put these results in the perspective of my previous works on the structure constants that were inspired, of course, by remarkable papers of Jan Goulden and David Jackson. First, let us define what we mean by structure constants. The basic idea is that we can view the symmetric group as an algebra by taking the multiplication as usual composition between permutations and to extend it bilinearly. Then we look at some reasonable subalgebras of this group algebra. Given basis elements C1, C2, etc., CR of such a subalgebra, they can be formal sums of permutations sharing some statistics. The structure constants are simply the coefficients that appear in the multiplication table. The most celebrated example, of course, is the case of the class algebra. Given a partition lambda of n, let us denote C lambda, the formal sum of all permutation of cycle type lambda. Then it is well known that the span of all C lambdas is a subalgebra of the group algebra of the symmetric group, and its structure constants C lambda mu nu give the number of factorizations of a permutation in the product of two permutations of given cycle type. Another important example is a descent algebra. Given a permutation pi of Sn in its one-line notation, P of 1, P of 2, etc., P of n, denote the defined descent set of permutation pi as a set of indices that indicate the positions where the values of permutations are decreasing. P of I plus 1 is less than P of I. Pi of I plus 1 is less than pi of I. So Solomon studied the descent algebras of all Coxeter groups that are generated by the elements di that are formal sums of all permutations of the same descent set I. Permutations in the case of symmetric group, here I speak about symmetric group. So, and the structure constants dij chi, as in the previous case, count some factorization, but this time not according to the cycle type, but to the descent set. So this subject admits many interesting variations. For example, we can study the peak algebra or the double coset algebra instead of the class algebra or the descent algebra. The symmetric group can be replaced by a group of signed permutations or any other Coxeter group. We also can define structure constants not only for two factors, but for many of them. All these various structure constants play important roles in different fields of algebraic and enumerative combinatorics, representation theory, maps, symmetric and quasisymmetric functions. Certainly, Jan Gulden and David Jackson made a significant contribution on the matter. However, in this talk, I will focus my attention only on two papers that were particularly inspiring for my personal works. So first, let me mention an important formula by David Jackson concerning the structure constant of the class algebra. So for an integer partition lambda I, let us recall the notation C lambda I, the formal sum of permutation of cycle type lambda I. And then we look at the numbers at the structure constants Cn lambda 1, lambda 2, etc. lambda r. That gives the number of factorization of the long cycle of length n into product of r permutations of cycle type lambda r. We also define the related numbers Cn, P1, P2, etc. Pr that gives the number of such factorization when only the number of cycles is fixed within each factor. So to be consistent with these notations, Pi is simply the number of parts of the partition lambda I. So David Jackson proved the following formula for the generating series for these numbers that can be expressed very elegantly in the terms or in the basis of following factorials. Many of my works were inspired by this formula, but I should admit that I had hard times understanding this formula in the original paper. But fortunately, back then, John Irving was very helpful in getting the formula on the first line here. So I started with this version. Another paper that is very significant to me is about the interpolation, the paper of Jan Gulden and David Jackson. It's about the interpolation of the structure constants of the class algebra and double coset algebra. So the double coset algebra is the Hecke algebra of the Gelfand pair S2n Bn, where Bn is a hypoctahedral group. I will not get into details. You can see here the definition of the cosets and the structure constants. What is interesting about these two sets of structure constants for the class algebra and the double coset algebra is that they are connected to the ring of symmetric functions. The structure constants of the class algebra allow to express the sum of products of sure symmetric functions in the power sum basis. In that sense, the structure constant of the double coset algebra allow to express the sums of products of three zonal symmetric functions also in power sums. We can see that these two formulas are indeed very similar, and getting a more general one seems as a natural question here. Jan Gulden and David Jackson write a more general formula involving Jack-symmetric functions. J here. Jack-symmetric functions are in fact an orthogonal basis of symmetric functions with respect to the scalar product that is deformed by an additional parameter alpha. What is important about Jack-symmetric functions is that they specialize to sure symmetric functions when alpha is equal to 1 and to zonal symmetric functions when alpha is equal to 2. In this expression for the sum of Jack symmetric functions, we can see some, in power sums, we can see some constants dependent on alpha that interpolate between the structure constants of the class algebra and of the double coset algebra. Jan Goulden and David Jackson make the very strong conjecture that these coefficients dependent on alpha have in fact a nice combinatorial interpretation similar to that of the structure constants. This conjecture is well known as the matching Jack conjecture and involves counting sets of matchings. As I told, many of my works have been influenced by these papers. So I will give a sample of these works. First, I developed a bijection between cacti, or basically speaking, the composition of orientable surfaces into polygons from one side, and some decorated cactus trees from the other side. This bijection provides a purely combinatorial proof of a formula for the structure constants of the class algebra that is almost identical to the formula of David Jackson. Certainly, we proved that these formulas are equivalent on some limit cases. Here you can see an example of object involved in the bijection. Here you can see cactus on torus, cactus on the sphere, and decorated trees from the other side. This work is a continuation of the work we started together with Gilles Schaeffer, and also these results have some roots in the work of Jan Goulden and Alexandru Nica. So, a new version of this bijection, this time for the hypermaps on general surfaces, not necessarily orientable ones, and involving some decorated trees, give us a formula for the similar formula, in fact, for the structure constants of the double coset algebra. As you can see, the object involved are much more sophisticated, and so is the resulted formula. This work we done together with Alejandro Morales. And finally, in the joint work with Kanonikov Promyslov, we get some significant progress on the matching Jack conjecture on the deformed structure constants in the case when at least one of the index in partition is a single part partition long cycle n. We also showed this conjecture is fundamentally a recursive question that can be described on the one hand using the operators on symmetric groups, and on the other hand, recursive bijection for edge deletions in graphs. So, over the last few years, I have been looking at similar results, but this time not for the structure constant of the class algebra or double coset algebra, but rather for the descent and the peak algebra. I should say also that these two algebra, descent and peak algebra, are in fact closely connected to the ring of quasisymmetric functions that is subalgebra of formal power series introduced by Ira Gessel. So now we need to introduce some definitions. First, we define labeled posets as an arbitrary partial order on the set of labeled vertices. Here you can see an example of such a poset on 5 vertices labeled with integers from 1 to 5, and the arrows showing the covariant relations. Then we define p-partitions and enriched p-partitions. P-partition and enriched p-partition is a map from the set of vertices to the set either only positive, either both positive and negative integers, such that F is compatible with the order on the labeled coset in the sense given here. So the difference between these two definitions is the possibility to have negative integers in case of enriched p-partition, but otherwise they're pretty much the same object. Next, define the generating function on labeled coset as the sum over all p-partitions associated to the labeled coset of monomials indexed by absolute values of p-partitions. One more important definition is, in fact, the variation of the labeled coset that is important for definition of other functions. So, given a permutation pi, in its one-line notation, we construct a special type of labeled coset on n vertices labeled by pi I, such that the covariant relations respect pi I less than pi j if and only if I is less than j. So we get such a chains like we have on the picture. As I told, they seems to be very important. For given pi, we can define the generating function of the labeled coset associated, labeled chain, we'll say, associated to pi, summing only over positive p-partitions is, in fact, Gessel's fundamental quasisymmetric function L pi. If one allows all enriched p-partitions with both positive and negative values, then the generating function of the labeled chain associated to pi is the Stambridge's peak quasisymmetric function. So, in fact, fundamental and peak quasisymmetric functions are related to descent and peak statistics on permutations. I already gave the definition of descent set of permutation pi. Now there is a similar definition of the peak set of permutation pi as the position where permutation reaches its local peaks. P of I is greater than both than P of I minus 1 and pi of I plus 1. While this set can be any subset of n minus 1, peak set is, in fact, peak Leckiner subset that is neither contains one nor two consecutive integers. So here we see the explicit expansion of fundamental and peak quasisymmetric functions provided by Ira Gessel and John Stambridge. Note here that these two expressions are in fact very similar and remind us of the expressions for Schur symmetric functions and zonal symmetric functions in the works concerning Jack symmetric functions and the matching Jack conjecture. We should note also that fundamental quasisymmetric functions depend only on the descent set of the permutation pi, and peak quasisymmetric function depend only on its peak set. So further, we can use the set indices for the fundamental and peak quasisymmetric function. The family of all fundamental quasisymmetric function is a basis of QSym, and the family of all peak quasisymmetric function indexed by all peak Leckiner subsets is a basis of a subalgebra of QSym called algebra of peaks. So now we would like to underline the connection of quasisymmetric functions to the structure constants of the descent and the peak algebra. I already defined before the structure constant for the descent algebras is basically the number of factorization of permutation into two permutations with given descent sets. In fact, we have very similar definition and similar result for the peak sets. Fundamental and peak quasisymmetric functions are directly connected to the structure constants of the descent set and the peak set, as shown this product formula on XY. Again, these two formulas are very similar and remind us of the work on the merchant-Jack conjecture. Actually, we built on this similarity and define a new kind of quasisymmetric functions that interpolate between fundamental and peak quasisymmetric functions. In the same vein as Jack symmetric functions interpolate between Schur and zonal symmetric functions. To achieve this, let us look again at the generating function for the labeled poset P. What we see is that this definition actually does not depend on the sign of the enriched P partition F. This is because of the absolute value in the indices of monomials in the definition of Stambridge. So our idea is to break this assumption and make monomials depend on the signs of P partition F by multiplying the resultant monomial by an additional parameter Q whenever the value of F is negative. So here I present our formal definition for Q generating function for labeled posets P. We see an additional factor Q that appears each time when the value of F is negative. One may already see that this definition covers the case of Gessel when Q equals 0, with only positive P partitions that are authorized, and the case of Stambridge for Q equals 1, where the sign of F is ignored by the absolute value. Now let us introduce Q fundamental quasisymmetric function for Q from the base ring K and permutation pi from Sn. The Q fundamental quasisymmetric function is Q generating series of the labeled chain associated to pi. Using this definition, we get the explicit formal power for series expansion of Q fundamental quasisymmetric function as follows. Two observations at this point. First, that Q fundamental quasisymmetric functions depends at most at the descent set of permutation pi. And the second one, that we immediately recover the explicit expressions for fundamental and peak quasisymmetric function when setting Q equal to 0 and Q equal to 1. So let me show you some important properties of Q fundamental quasisymmetric functions. First of all, we can start with an easy one, that Q fundamental quasisymmetric functions, in fact, are quasisymmetric functions because of their definitions by the enriched P partitions. So let us move now to the more advanced properties. I also define an enriched Q monomial by the following formula. This is not exactly the generalization of monomial quasisymmetric functions, but rather the essential quasisymmetric function by Hoffman for Q equals 0, and also enriched monomials of our FPSACT 21 paper with Dari Greenberg for Q equal 1. In fact, these enriched Q monomials can be expressed in the following way with the classical monomial quasisymmetric functions in their basis. When Q from the base ring is such that Q plus 1 is invertible, then the previous formula connecting enriched Q monomials and classical Q monomials can be reversed, getting this formula connecting classical monomials with enriched Q monomials. And as a direct consequence, we have that enriched Q monomials are basis of QSim for invertible Q plus 1. For example, if we set the base ring K as a set of complex numbers, it means that the enriched Q monomials are always the basis of QSim, except for the case when Q is equal -1, that is the generate case when almost all enriched Q monomials are equal to 0. So we also have a nice expression of previously defined Q fundamental quasisymmetric function in this new basis of enriched Q monomials, as you can see here. For those interested in antipodes, I have also, and for invertible Q, I also have a nice expression of the antipode of Q fundamental quasisymmetric functions is in this formula. Now let us move to the most interesting question. It is our Q fundamental quasisymmetric function a basis of QSim? We know for sure that for Q equals 0, it is true, as in this case, Q fundamental quasisymmetric function reduced to Gessel's function. We also knew that it is not true for Q equal 1, as Stembridge's big quasisymmetric functions are not the basis of QSim, but of subalgebra of QSim. The case of Q equal -1, the degenerate case, doesn't work as well. What happens in the general case? Before moving to the general theorem, let us work out a little example for small values of n, for n equals 3. Here I expressed Q enriched Q monomial in terms of Q fundamental quasisymmetric functions for n equals 3, and we see that the Q fundamental quasisymmetric function behave as a basis, except in the case of Stembridge of Q equal 1, the degenerate case Q equal -1, that is not surprising, and then also for the two other roots of unity. So this little example gives us the pattern on a unit circle. Actually, we prove the following theorem. If we set the base ring K to be the set of complex numbers, then the family of Q fundamental quasisymmetric functions is a basis of QSim, if and only if Q is not the root of unity. We prove this theorem thanks to the characterization of the transition matrix between Q fundamental and enriched Q monomial quasisymmetric functions. Actually, we show that the determinant of this matrix is non-zero if and only if Q is not the root of unity. More precisely, let Bn be the transition matrix between Q fundamental and enriched Q monomials. Then, using our formula, I compute for n equal 4 a small matrix B4, as you can see here. What we noticed is that this matrix is in fact block triangular matrix, and it block triangular, we have one block here, the other block here, and one more block here. And we have some interesting repeating patterns. You see this one is equal to this one, etc. So I will not enter in all the details, but thanks to all these observations, we derived a recurrence formula for the determinants. I also made the details here, but in the final formula, you can see Q factorial numbers that are non-zero if and only if Q is not the root of unity. Now, before I finish my talk, let me one more time turn to the structure constants of the descent and peak algebra. Here I say Q deformed structure constants, but I have a little property that explains why it is in fact again coming to the descent and the peak algebra. Let us come back to the product formulas. By rewriting the product formula for fundamental quasisymmetric function and the peak quasisymmetric function for the product xy, we can see the general form in terms of permutation factorizations. So in fact, there are all the terms, they are not grouped, and we cannot see any coefficients, just like this. And the natural question to ask here is whether we have a natural way to extend this formula to the case of Q fundamental quasisymmetric functions. So the answer is yes. Here is the proof of Kyle Peterson for peak quasisymmetric functions. Not this one, but the one with the structure constants. In fact, is only relies on the underlying enriched bipartitions even before the application of generating functions. So if we make Q generating functions, it doesn't change the method, and it's possible to extend here. So strong with these previous remarks, we can see two more interesting facts here. First is if Q is not the root of unity, Q fundamental quasisymmetric functions are the basis of QSym, and we have this Q fundamental product formula that we can see here on the product xy with the structure constant involved that are exactly the structure constants of the descent algebra. And the second interesting open question, and here I will finish my talk, is that what happens for the other Q's roots of unity? For Q equal 1, it's the only value that we know. This formula, this product formula reduces nicely to the product formula of K, the peak quasisymmetric functions, and certainly the structure constants that appear in that case are the structure constants of the peak algebra. So is it possible that there is some nice formulas in the case when Q equal other roots of unity but 1? So thanks for your attention.
Are there any questions? Yeah.
No, this is interesting because these are the structure constants of the descent algebra. Those are exactly the number of factorizations of permutations of descent of a permutation of descent set J in the product of two permutations of descent set I and J, no Qs there. It is surprising, and that's why.
So I'll just repeat that question was whether that depended on Q.
Yes.
Yeah, so the next question, if you could repeat it, if there is a next question. Yeah.
Yes, Alejandro.
So is there a way to like control descent sets and cycle types maybe? Like a way to, I don't know, find some unit, like some links between the two.
Descent set and
cycle type?
And cycle type. The question was, is there some way to the descent set and the cycle type of permutations? I don't know the answer. Probably, I think it's independent statistics. It's completely independent statistics on my thinking now, but one can never say no without thinking.
Is that formula like does it have the cancellation free or?
No, it's some. In fact, we used some play on indices, some combinatorics of indices, some exclusion, the things like this before. So it's some chain of different. We constructed some theory for this Q stuff, and then we saw that some nice properties can be saved. And moreover, what was nice for us that we saw that exactly like David and Jan made in the case of the match and Jack conjecture, there is a way to make the link, the bridge between Ira Gessel's and John Stambridge quasisymmetric functions, and before seemed to be different cases to make some natural background for that.
The question was whether the antipode formula was translation free, actually. So, is there more questions? Okay, so we'll thank the speaker again.
Thank you very much.